again and welcome back to NA and ME with Yogesh Bahadur. Module 3. Well, it's been a heavy heart that we have all had as we watch the disturbing scenes and the rise of coronavirus all across the world. For me particularly, it has been very disturbing to see the scenes, especially coming from New York, because I was there just 3 months ago on a vacation, and that was after 30 years that I did a bit of my education in naval architecture. And I worked in the US for a good 7 or 8 years in a small little town called Newport, Rhode Island, which is known mainly for building of yachts. In those days, there was a Navy shipyard which doesn't exist there anymore. That was kind of a seat of learning for me because it was my first shore job. Got this grand opportunity to work in different departments, starting with the systems engineering department. The system engineering department deals with designing and laying out of pipes and piping systems. And as I said in my earlier segments, the Navy and the Coast Guard ships particularly are very dense in the way the piping and all is to be arranged. There are a lot of bends, a lot of, routing spaghetti of pipes over there. What does that do is that the losses, the frictional loss that are there for the piping systems are a lot more than what would be perhaps now as I'm doing the power plants, the thermal power, hydropower plants, where the piping is pretty big and you've got football fields of area to lay it on. But on the ships, the area is very small. And so we come at more of complication in determining what would be the flow, what would be the pipe sizes, and how to route them. And every time you route or reroute the pipe, because if you are going and putting the piping here and the HVAC guy is coming from the other side, and then you have to again turn the pipe. All these things are continuously changing conditions of the piping flow and hence the capacities that we are working with. And today's lesson is somehow I'm trying to build it, reviving that knowledge and somehow dovetailing it with what you are learning in fluid mechanics or what you have learned so far. And then also to work a little bit in reverse to see how we can use that knowledge if you were placed in that similar position to be designing or working in a company, in an organization where you had to do something a little more than just maintaining the piping systems. Okay, so in a way also, I am deriving all these old memories and experience and revisiting some of the books. I have more time, and when we have more time, we can think a little deeper. So the overall agenda today is a hydraulic exercise to determine the pumping capacity and what will be typically the most optimum power that the pump is going to be operated at to do its desired function of pushing the water to its worst case duty of the firefighting system. And the worst case duty of firefighting system is pushing the water to the last of the hydrants further away from where the pump is. So we will be understanding what is the static head and what is friction head. Static head we already discussed even in the last episode, the positive suction head or the negative suction head in case the water level is below the level of the pump. And then there is a frictional head of the pumping system, which is due to the roughness factor of the pipes, which is dependent on certain coefficients of friction that were derived from various equations like the Darcy's equation. And then we have another important aspect which is going to have a bearing on the frictional head component, and that is the viscosity of the fluid. And the viscosity of the fluid has a relationship to the density and the velocity of the fluid, which is going to go, and it's determined by the Reynolds number. We'll also talk about one of the very important terminologies that is used in practical hydraulics on the design tables, and that is the L by T that you see in the Darcy's equation is called the equivalent length. Basically, it represents how much of a pressure drop where there'll be in a pipe of, say, 1 meter length. And then we say that the pressure drop in typical fittings of the same diameter is going to be a function of the straight length of a single pipe. For example, a fitting like an elbow can have, let us say, 1.5 times the pressure drop of a straight length of 1 meter. And maybe we can say that a T can, because it's going at right angles, it can have a pressure drop of 3 times of a pipe length of 1 meter. I will show you later on the charts for various type of fittings, how the equivalent length varies for the fittings of the same diameter. And then we will see how this equivalent length go into the calculation of the pressure losses in the pipes and the fittings. Let's take this firefighting system we have in front of you, and you can see there are 3 pumps at the bottom of the ship, and these pumps are pumping water to different branches. You can see that some of this water is going into the tanks within the engine room too, within the pump room. Maybe there are some hydrants inside the machinery spaces, and then this is going and giving water to certain maybe sprinkler systems on the various accommodation and other decks. And then you can see this is going into other hydrants right across the length of the ship, and there'll be a closest point from the pump, just putting the water to some tank close to the pump, and the farthest point will be, let us say, the farthest hydrant wherever it's located. With this, what typically you will do if you are sitting on the design table is that you will just take each and every little section. A little section means the point from where the line is branching out from the main discharge line to that point of discharge. And for each of these, you put the values of L and D on an Excel sheet. You just calculate the number of fittings and the length of the pipe. It's typically, I will show later on in an actual calculation. Basically, we segregate each of the diameter sections. Let us say we have got 20 millimeter. The lower diameters will be at the further away, maybe on the poop deck or on the forward and the aft of the ship where the hydrant is going. And the higher, the bigger pipes, let us say 200 millimeters or even more, they're going to be more closer to the pump, depending on the size of the ship and the capacity of the pump. Now, in Excel sheet, the complete piping is mapped out in terms of its L by D and this equivalent length. And once we have the equivalent length, plugging it into these equations, we get the total frictional loss. And this is the most simplistic way of explaining this. So here, this is the typical Excel sheet, or how the inputs are coming into your computer program. You can see that what is the pipe nominal diameter, what are the different schedules of pipes that are being used. There's a schedule 40 pipe, and there's a schedule 80 pipe, and then we can have so many length of so much for one diameter of pipe. Another diameter of pipe we have some other length. And just to remind you, in the diameter we are considering the internal diameter, because that's where the passage of fluid is taking place. And when we get the length of the pipes, then we also list out all the fittings. Since this is a typical case, the number of fittings is very low, but in actual ship you can have 500 or thousands of fittings and valves in these systems. This is how it will be. On the suction line there are so many, in the discharge line there's so many. When we come to the valves, the data is given by the valve manufacturer. The valve manufacturer gives you the pressure loss in the valve, and we just plug that into your software. Purely laminar flow is not possible in case of most of the piping systems. The flow in general will be more towards the turbulent side, and what we are doing in design of the pipes is that we are limiting the turbulence to manageable levels. What is a manageable level? A manageable level of turbulence is a point where you will not hear the knocking in the pipe. If you have ever sailed in the ships, have you heard the knock, tock, 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 the sound that comes from the pipe? That is when something has gone wrong. Some excess water is going, or there's an airlock, and we don't want to have that. And so how do we do that? We do that by maintaining a certain maximum velocity in every diameter of pipe. In case of water, I think the limitation of velocity is somewhere like 1.5 meters per second, and in some cases they are taking maximum of 3 meters per second, if I remember right. This 1.5 meters per second basically comes out from the Reynolds number itself. This data is available in most of the fluid mechanics hydraulic handbooks which are available in the market. Also, it's available on the net these days. You can just surf and you will find all these data available. These are some of the equations that the Reynolds number is associated with. All that we have to do here is just to see how it is related. Basically, there are three parameters. That is the rho, the density, the velocity of the fluid, and the diameter of the pipe. And it's just common sense. We can say that if a thicker fluid, a more syrupy fluid, is going to have less velocity for the same pipe diameter, let's say water is going to flow more readily, more than a thicker fluid, say oil. If we have the Reynolds number, we can know the diameter of the pipe. If you have the diameter of the pipe and the Reynolds number, then we can find the velocity. So that's how these equations are kind of interchangeably used. Generally, what we are doing here is, by limiting a certain velocity, we are actually finding the design diameter of the piping flow. The inputs were the piping lengths of different diameters. Then we listed the fittings. We put the pressure loss values of the valves as given by the manufacturers. We said that the fluid regime was turbulent, and what we get as outputs is the frictional head losses in the pipes and fittings in the various piping sections, and we get what we were looking for. We have got the flow through each and every exit point of the hydrants, and in the worst case, the frictional losses inside all of the pipes when all possible hydrant sprinklers are running. And in the worst case, we have got the flow, and we have calculated the total head loss in the worst case when everything is working, and we have determined the maximum the flow that is going to be given by the pump. With my face up here, the rest of the module is purely technical, and it goes with the slides. I want to thank all of you who are watching, and this is a permanent. If you're not watching today, you can watch tomorrow, and I would really request the people in the faculty and in the think tanks of the companies to just pass these things on, and it's going to add to your efforts in whether you are taking the e-educational classes for cadets or for the seniors, for the chief engineers and the second engineers, the fourth, and so on. And also for all those people who are just sitting right now and planning their lives to say, if after this I can do this, I can do this. Be my guest, and your comments and your feedback, ideas on what more we can do to make it more of value, also to within your organizations and your institutions. I will be very thankful if I can have your comments. Goodbye for now.